Okay, so we're going to talk about equilibrium. So, again, a brand new topic here where we apply everything, but we learn a bunch of new stuff. So, this chapter is going to go fairly quick, so you want to stay up with it and make sure we are following along each day and asking questions. All right, so equilibrium. Equilibrium is a balancing, like it sounds like you control the equilibrium in your body so you balance and you don't fall over. Usually it's found in it is in the eustachian tube in your ear. That is the control center of balance. But for chemistry, we're talking about what's going to balance out. So in reactions, what we're going to balance are opposing forces, opposing reactions. Okay. Oh, my pen does not want to work. It is opposing my writing that down. So there we go. We are going to balance opposing reactions. Okay. So what's going to happen is that we want a chemical equilibrium. If that is reached, which we want a lot of times, and we'll establish why, opposing reactions occur at equal rates. So it's about how fast the forward reaction is going compared to the reverse reaction. So I always give this analogy kind of like, okay, here's city A, and that's our reactants, and then they're going to go over the bridge into city B. Now, at any given time, we may start over here with 100 people, and then they start to filter over to the bridge, and then we may end up with, okay, now we have 80 people here and 20 people left who went to city B. So these are what we're talking about with the moles, right? How much goes, okay? But again, it always has to add up to whatever we have for reactants. You can't create or destroy matter, so whatever's there has to still be there. So you see 80 and 20 adds up to 100. You may lose another 20, and now it's 60-40 each step of the way over time, right? So over time, this is happening. Now, when will equilibrium be reached? Equilibrium is only reached when the rate of who is going this way and the rate of going this way, so we can reach, whoops, I don't really want to draw an arrow there. So we want to reach equilibrium is when we have the same amount of people leaving or the same amount of molecules going from reactants, say it's 10, and the same amount going back to the other side to become from reactants to products, products to reactants. They're going exactly the same rate. Then what's going to happen? There is no net or overall change. Okay, so what that means is, yeah, there's change going on. So it's still what we call dynamic, but it is not actually noticeable. So if you were looking at, you'd say, okay, well, if it were at equilibrium and I reached that I had 50 people, I don't want to do even, sorry, I meant 80 people over here and 20 people over here. Well, when 10 leave and 10 come back, guess what? There's still 80 people over here as reactants and 20 over here as products. Understand what I'm saying? So once we reach that equilibrium, it's going to make the amounts on the side the same, but not equal or equivalent in any way. Okay, they could be equal, but they may not, of course, most times. All right, so that's the explanation of equilibrium. So that's what we're studying. We need to define equilibrium, which we did. Equilibrium constant. So an equilibrium constant is where that equilibrium is reached. Okay, so how do we find that? Well, we write it as an expression first, and then we can solve it. Okay, now whenever you see K, that is the equilibrium constant. Remember I told you it made a difference. It has to be capital. So capital K, as in the other constant, remember in rate laws, was a lowercase k. So that's why I was making such a big deal about it. Now this, the little subscript here, means concentration. So this is an equilibrium constant based on concentrations. We can also have Kp, which is based on pressures. So you're going to get atmospheres. Or you can also say a generic thing. Okay, so Keq. EQ stands for, you guessed it, equilibrium. And equilibrium can be either Kp, Kc, depending on what variables you're given. So it does not have to be as specific. So Kc and Kp are very specific. Keq is the catch-all for everything at equilibrium. All right. So what we learned is that the rate of the forward is going to equal the rate of the reverse. Okay, so what we're saying again is the rate going forward is the same as the rate going reverse. So the reverse and forward reactions, and you guys know or forward means reactants to products, reverse means products to reactants. All right. So how do we set these up? They are really easy, to be honest, if you let them be. So just follow the formula. It's always the concentration of the products divided by the concentration of reactants, and they're both raised to their coefficient. So you need a balanced equation to do this. Now, products over reactants. So I always say balancing equilibrium is P over R. So PR, I always think in my head public relations, and public relations people are keeping the balance. They're trying to make sure the public, hey, you're happy with your products and whatever. Okay. So that's kind of where my head goes to memorize it, although you guys don't because it's right in your book. As usual, all your formulas, you can see here's the K based on concentration, K based on P. Now, K, C, and KP can just be generically used as EQ if you know you have those. But we do have to be very specific because we're going to relate KP and KC, all right? And they're easily related with the formula. All right, so we're going to express this. Now, look at this question. It just says expression. There's actually not going to be solving here, okay? It's just going to be writing the K. So K of C equals, because we're going to use this expression. And so what we're going to do is the products. So we go over here to the products, and here's the other catch that I haven't told you yet, okay? There are homogeneous and there are heterogeneous reactions, as you see in the objectives. Homogeneous means they're all the same phase. And then heterogeneous means you have a gas and then maybe a liquid in the same reaction, okay? This one right here is homogeneous because you have all gases, so it's homogeneous. I'm not going to write it all out. This one down here, if you just skip down a little ways, you have a solid, a gas, a liquid. Whoa, that's really heterogeneous, right? Because you have one of almost every phase there. Wow, nice. All right, good example. All right, so what you have to realize then is also those gas and liquids apply, so are going to matter here. In equilibrium, the ones that we can control and make affect the rate or the constant, I'm sorry, I was still thinking about rates, are the gases. Okay, so we're going to ignore solids and gases. So you're going to ignore solids and gases when it comes to the rate constant. So since these are all gases, we're going to include them all. So we go to the product side first. We put it in brackets because that means concentration of NH3. You may make sure you copy it right. If there's a charge on it, you have to put it on there. If it's an ion or not, don't put it. And then it's raised to the 2 because that's the coefficient. We're going to divide that by the reactants. And by the way, the product of the products and the product of the reactants. I know that may sound confusing, but we're multiplying, okay? So the N2, and you be careful when you're writing these because N2 and H2 get mixed up quite often. It is raised to the 1 concentration. And again, we're multiplying, so there's no need to put any signs in between them. And I think the reason a lot of people add it there is because it's in the equation, but it is not in this when you do the K expression. H2 concentration is raised to the 3rd, so it is going to be cubed. So that is my answer for A. That is an expression. So when I ask you just to express it, I'm just expressing. That's it. That's how I would solve for it. Okay. But next problem, B, is going to say, okay, well, if I give you the concentrations, can you calculate Kc? Well, of course we can, because again, this is just math. So Kc is what I don't know. And then I'm just going to plug everything in. And I've got the equation right here, NH3. Well, where's my NH3? Well, it said respectively, right, in these orders. NH3 is the very last one, right? So that is 0.15 molar. And what do I have to do? Here's one of the biggest mistakes is that you just don't copy it down right. There's a squared there, all right? And then we got N2, and that is the first one, the 0.25. And you got to be careful because this one is only raised to the 1, so you don't put anything. So just make sure you've got the right one with the right one, okay? And then finally, hydrogen is the 0.10, sorry. You got to be very careful because there are tricky numbers like that, 0.10 or 0.01. You got to be very careful. And it's cubed. All right, now, when you do these, I think a lot of people, it is, again, the calculation part that gets you. Most people do the squaring okay. But again, the more work you show, the better. And especially on these, I just find there's a lot of errors at times in the calculation. So it's better so you can lose less points if you mess up something. The squared button is right there, so you can use that. Or you can raise it to the square. There are no issues with the syntax here like there is on other problems with scientific notation. Theoretically, I could round to sig figs, but I'm not as worried when we're squaring it here. So we're going to go the 0.25, and then I'm going to take 0.1 and cube it. So that means I'm going to raise that to the third power, okay? And that is 0.001. Now, some of you guys, calculator buttons and whatever, you can take 0.1 times 0.1 times 0.1. I mean, that just takes longer. Obviously, it's the same answer. Now we're going to have to simplify. I usually just try to do this real quickly and say, okay, 0.25 times 0.001 is this, just at least to show my work. But I didn't even have to do that because I could just take 0.0225 and divide by 0.25 and then divide by 0.001. It'd be the same thing as taking 0.0225 divided by the number I got there. And whoa, that's a weird looking number, isn't it? 90. And then I need to know, do I need extra sig figs? Do I need to put a point? What do I need? Well, all of these have 2 sig figs. So guess what? We got to go to 2. So we do have to put the point here. You have to, because we want those 2 sig figs. Now here's the thing, guys. This is a hard one. K has no units. It's just a constant. It is one that makes me crazy. It's kind of like mole fraction. Remember that? Where you guys are like, I want to write something. K. And I like K, though, that it is this because I just go at the end. I go, K. I don't have a unit. All right? So it is just a value. So that's a little different. And lastly, we got a couple things here. We already answered, is it homogeneous or heterogeneous? Because they're all the same. This second problem here, you already know it's heterogeneous because you have a solid, a gas, and a liquid. So you're going to try number 2 and then come back, pause the video and come back. Whew. All right. All right. Oh. Sorry, Miss Kane came in and we were talking for a sec. So while you guys were paused. So here we go. I forgot to tell you, though, or I didn't. I told you ignore solids and gases and liquids. Ooh. Oh, my gosh. I put, you know what? Wow. Let's learn this the right way. Solids and liquids are ignored, so it's my fault if you mess this up. So we're going to finish this. The products are first, but guess what? We don't have a product. We got to ignore this because it's a liquid. It's not going to affect the equilibrium. So we're going to write nothing here except for we do have to hold it with the 1 because that is a numerator. The titanium we're also going to ignore because it is a solid. So we don't have to write anything yet because we do have another reactant. This is the only one that gets included. So we have the chlorine in concentration brackets, and we're raising it to the 2, which is the coefficient. So that is our equilibrium expression. So all we're going to do now is plug the numbers in. This time we're solving for the concentration and not the K. You can see the K does not even have a unit.